Welcome to Visual Algebra Lecture 2.2, Cyclic Groups. We've seen cyclic groups before, but now we're going to formally define them and devote this lecture to studying them. Along the way, we'll encounter a new way to visualize finite groups called a cycle graph, which will be handy to have at our disposal going forward. First, a formal definition. A group is cyclic if it can be generated by a single element. A good way to think about these is that finite cyclic groups describe the symmetries of objects that have only rotational symmetries, like the ones shown here. We'll talk about infinite cyclic groups later on. We have seen three ways to represent cyclic groups in the last lecture. First, by roots of unity. So Cn is generated by e to the 2 pi I over n, which is a primitive nth root of unity, and it is the set of all nth roots of unity. This is a subgroup of the complex numbers. Next, by real rotation matrices. So Cn is generated by this rotation matrix, cosine theta, negative sine theta, cosine theta, for theta equals 2 pi over n. And finally, by complex rotation matrices, which is probably the least familiar of all of these for most of you. So Cn is generated by Rn, which is this diagonal matrix where the 1,1 entry is an nth root of unity and the 2,2 entry is its complex conjugate. As I said, this is going to be our preferred rotation matrix going forward, and we'll learn more about it later. Let me now make a definition that is mostly about notation. Cyclic groups can be written multiplicatively or additively. I'm going to write the multiplicative cyclic group as Cn and let this be the set of powers of R. So think of R as an abstract element like a rotation. So Cn is 1r, r squared up to r to the n minus 1. I think it's fairly self-explanatory. Here are some Cayley graphs for n equals 2 and n equals 3. Notice it doesn't matter how I embed or lay these out. Here, it's laid out in a counterclockwise direction. Here, clockwise. Here, in a row. These all represent cyclic groups. It should be clear that Cn has the following presentation. It's generated by R, such that r to the n equals 1. It should be clear that the following is a presentation for Cn. It's generated by r, subject to r to the n equals 1. Now, r isn't the only possible generator. For example, C5 is generated by r squared. Just look at the successive powers of r squared. We get 1, r squared, r to the 4th, r, and r cubed. So we get everything in C5 from just r squared. Now think, do you have a conjecture about which powers of r generate n in terms of k and n? See if you can take a guess, and we'll answer it later. Cyclic groups can also be written additively, and I will let Zn, this boldface Zn, denote the set of numbers 0, 1, 2, up to n minus 1, where the binary operation is addition mod n. Notice that the identity element is 0, whereas the identity element in Cn multiplicatively is 1. Here are some Cayley graphs. They look just like the ones in the previous slide. It's just now we have numbers instead of the corresponding power of r. Notation for cyclic groups is a little bit inconsistent. Cn and Zn are both used, but also just the regular Zn is used. And you also might see Z mod NZ or Z mod, this is n in parentheses. This is from ring theory. All of these are used. These two things have specific meaning. Some people like these because Z mod n or Z mod p is reserved for the p-adics, which we are not going to see, so there's no confusion. Sometimes people write Cn and they let the elements be numbers, or they write Zn and they let the elements be powers of r or powers of a. I will use Cn for powers of r multiplicatively and Zn for numbers throughout this course. I think it's important to be consistent with this notation. We can write a group presentation additively. So Zn is generated by 1 such that n dot 1 or n times 1 is equal to 0. And n dot 1 is exactly what you think it is. It just means 1 plus 1 plus 1 n times. So this is the analog of the additive analog of saying like r to the n equals 1. Note, of course, that 2 generates z5 for the same reason that r squared generates c2. So if you just add 2 to itself successively, you will get all of the numbers 0 up to 5, 0 up to 4 mod 5. It's important to emphasize that even though these are isomorphic groups, Cn and Zn are not equal. We should never write Cn equals Zn. Zn is a set of numbers. Cn is a set of powers of r for some abstract symbol. We can say that Cn and Zn are isomorphic. I'm going to now answer a question that I posed a couple of slides ago. First, recall that the greatest common divisor of non-zero integers a and b, you probably know what this is, but let me formalize it. It's denoted the GCD of a and b, but it is the minimum that ax plus by can be, where x and y are all integers. This is a basic fact from number theory, but it can be taken as the definition. Moreover, a and b are co-prime or relatively prime if their GCD is 1. So this is equivalent to saying that we can write ax plus by equals 1 for some integers x and y. Okay, here's a proposition. Any number k from 0 up to n minus 1 generates Zn if and only if it's relatively prime to 1. Equivalently, Cn is generated by zeta n to the k, or if you prefer, we can write this as r n to the k. So you can think of r just as the abstract rotation, or you can think of it as the actual complex number zeta n, if and only if zeta n to the k is a primitive nth root of unity. So let's prove this. So let's do the backwards direction. I'm going to leave the forward direction as an exercise. It's not much different than the backwards direction, but let me start with this. So let's assume that the GCD of n and k is equal to 1. How would we show that k generates n? Well, k generates Zn. K generates Zn if some multiple of k is equal to 1, right? Because if we can get 1, we can get everything. Conversely, if we miss 1, we won't get everything. So we want to show that 1 is in the subgroup generated by k. And that, remember that that's just 0, k, 2k, 3. It's an infinite list, but it's, of course, going to wrap back around. So we want to show that 1 can be written as some multiple of k. So how do we do that? When I say 1 is some multiple of k, of course, we're working mod n. And so what I really am saying is that 1 is equal to k, some multiple of k, so ky for some y in some integer y. So what can we assume? We can assume that the GCD is 1. So since the GCD of n and k is equal to 1, we can write 1 equals nx plus, let's say, ky for some x and y that are integers. So we can write this, and now do you see what to do? Let's reduce both sides mod n. So if we reduce mod n, we get 1. And I'm going to write subscript n. I should have put a subscript n up here as well. I said it. So 1 is equivalent mod n to nx plus, well, what happens when you reduce this mod n? Well, nx is a multiple of n, so that just goes away, and we're left with ky. So 1 is equivalent mod n to 0 plus ky, or just ky, and that's exactly what we wanted to show. So again, this all boils down to this definition of the GCD. So I'm going to leave the forward direction as an exercise. And it's not much different than this. So suppose k, I mean, it's basically running this in reverse. So suppose k generates Zn. That means some multiple of k is equal to 1. So let's say that's equal to k times y equals 1. And now you want to reconstruct this. So I'll let you figure that out. I want to say a few words about Cayley tables of cyclic groups. It doesn't matter whether we write things additively or multiplicatively, but sometimes, based on the context, it's more convenient to write one versus the other. So here, I'm going to write them additively because it just avoids me having to write r a whole bunch of times here. And notice that modular addition has a nice visual appearance in the Cayley tables for cyclic groups if we order the elements in a sensible order. So here are two different ways to write the Cayley table for Z5. And notice that you have these patterns of the same number, and it's not hard to see that this is going to hold for any n. Now, if you mix them up, of course, you destroy that pattern. So if I mix these up in this order, it looks like this, and you might recognize this, that this was one of our mystery Latin squares from the previous chapter. Remember, I gave you 2 Latin squares on 5 elements, and I said one of these represents a group, the other one does not. This is the one that did. Next, I want to talk about minimal versus minimum generating sets, something that I mentioned in the previous chapter. There are many ways to generate the cyclic group of order 6. We know that it's generated by 1 and also by 5, because these are the two things relatively prime to 6. But notice it's also generated by 2 and 3. And why is that? Because from 2 and 3, if I take 2 plus 2 plus 3, I get 1, and now I have a generator of Z6, so I have everything. Same with 3 and 4. I can write, if 3 and 4 are in my subgroup, I can write 4 minus 3, which is 1, and that generates, and so 3 and 4 together must generate. So here's a bunch of generators. And here are Cayley graphs illustrating both of these. So this first one is generated by 1, and this next one is generated by 2 and 3, which is shown right here. Notice that this looks a lot like the Cayley graph of the triangle symmetry group. The only difference is these inner circles go counterclockwise, the same direction as the outer circles. So here, green, blue equals blue, green. But for the triangle symmetry group, if we went, it was red, blue equals blue. We had to go backwards. This example nicely illustrates the difference between a minimal and a minimum generating set. So I mentioned this in the first chapter, but let me remind you again. So given a group generated by S, we say that S is a minimal generating set if any other proper subset does not generate. That means if we remove anything from S, it no longer generates. So this is an example of a minimal generating set, because if we remove the green arrows or the blue arrows, it no longer generates. However, it's not a minimum generating set because there is a smaller generating set, namely 1 right here. So we say that a generating set is minimum if it's minimal, and all other minimal generating sets T are at least as large. Finite groups always have at least one minimum generating set. They have finitely many subsets. So take the ones that are generating sets and then take something of the smallest size, and there you go. But what about infinite groups? The fact that I'm asking you this strongly suggests that the answer is no. So let me give you a hint. I'll let you think about it, and we'll come back to this in a couple lectures when we talk about abelian groups. So let's take the rational numbers, and I'm going to take away 0. So I'll have notation for this later, but for now, let me just write this. Q take away 0, and the binary operation is multiplication. And compare this to the rational numbers under the operation of addition. And think about what a minimal or minimum generating set for one of these might look like, and if they necessarily exist. Let me say a few words about infinite cyclic groups. There's only one of them up to isomorphism. You'll see why shortly if you don't already see it. If we write them additively, then the infinite cyclic group is just the integers. So generated by 1, subject to no relations. The multiplicative infinite cyclic group is just all powers of R. So it's generated by R, subject to no relations. And I'm going to write that as C infinity. Several of our Friese groups were cyclic, infinite cyclic. Remember the ones generated by a translation or a glide reflection? They had this infinite line Cayley graph. And there are only two choices for a minimum generating set. The integers is either generated by 1 or by -1. So if you choose -1, you get the same Cayley graph. The arrows just go in the opposite direction. However, there are many choices for larger minimal generating sets. Here's a Cayley graph using 2 and 3. And I encourage you to think about not only what other minimal generating sets of size 2 there are, but also what minimal generating sets there are of size 3. So as a hint for this, 30 is equal to 2 times 3 times 5. So if you mix and match some primes, if you take 2 times 3, you take 3 times 5, I don't want to say too much, and 2 and 5, you can get a generating set of size 3. That's minimal. I want to finish this lecture by introducing a new visualization of groups called a cycle graph, or sometimes an orbit graph. This isn't as ubiquitous as a Cayley graph, but it's useful to have in tandem because it really shines the light on different structural aspects than a Cayley graph does. For this, we need the definition of an orbit of an element, which is just the cyclic subgroup that it generates. So it's the set of all powers of G, where the element is G. Now remember that the order of a group is, we use absolute value symbols, and it's just the order of G is just the size of the group as a set. We also want to talk about the order of an element, so we'll use the same symbol. So this is the order of little g, and by definition, we're going to say that that is the set, or it's the order of the subgroup generated by G, or the order of the orbit. So it's how many distinct powers of G we have. Notice that the order of G is equal to the minimum K, minimum integer such that g to the k is the identity, or infinity if there is no such k. So that's how you should think about this. And I think the term orbit is indicative of the fact that if you think about a Cayley graph and you just map out powers of g, it looks circular, or you can think of it as circular. It's an orbit. We can visualize the orbits, all of the orbits in a group, by the undirected orbit graph or cycle graph. This is best seen by an example. So this is the Cayley graph of the square symmetry group that we saw in the previous chapter. And here are the 8 elements, and here are the orbits they generate. So notice that 2 elements, r and r cubed, generate the same orbit, and that should make sense as to why. And I don't want to bias either of these as generators, as the best generator, because think of this as counterclockwise, this is clockwise. So that's why we don't put arrows on the cycle graph here. So the cycle graph consists of all maximal orbits. And by maximal orbits, I mean orbits that are not contained in any larger orbit. So a non-example, so this orbit contains 1 in r squared, it's in this larger orbit of size 4, so we don't need to add these arrows. That doesn't really add any more information. So here, any 2 of these orbits intersects trivially, and you can read that off of the cycle graph. I guess you won't really see what I mean by the intersection of orbits until we see examples where there's a non-trivial intersection. So we'll see this for a bunch of groups. We'll see that, and it'll help us understand certain structures. So let's finish with one more example. Here is a cycle graph for the quaternion group Q8 that we first saw in the lecture on Cayley tables in the previous chapter. Here are the 8 elements, and remember that in this group, I squared equals j squared equals k squared equals -1, which means that I, j, and k and their negatives all generate orbits of size 4. So here they are. I and negative I generate ±1 ±I. Same with, analogously with j and k. So there are, -1 generates ±1. This is not a maximal orbit. So notice that this is non-maximal. And of course, the orbit generated by 1 is not maximal either. So there's 3 maximal orbits, and they are right here. And you can see those orbits right here. So the orbit generated by, or containing I is in red, the one containing j is in blue, and then the one containing k is in purple. Now, it's not standard to put colors on here. I like to do it just to emphasize, or just to make it unambiguous. If you go to the Wikipedia page on small finite groups, you'll see cycle graphs for all of them. They typically don't have colors, because it's kind of understood by symmetry that, yeah, this is a 4 cycle and that's another 4 cycle. But that's not precise. That's assuming some maturity from the reader. So when possible, I like to add colors. It also makes it look pretty. Also notice here that these 3 orbits, they all intersect in these 2 elements right here, 1 and -1. And you can see that here. If you take any 2 of these 4 cycles, they intersect right here. So I think I've said most of these remarks. We've colored the edges to eliminate ambiguity. It's optional. We left the edges undirected. I don't want to bias I or negative I to be a generator. All the maximal orbits have size 4, and they all intersect in a size 2 orbit. Okay, so that's a good place to stop. In the next lecture, we're going to look at dihedral groups. These are the groups that this is a general class that contains groups that we have been calling the triangle symmetry group, the square symmetry group, and the hexagonal. They are symmetry groups of regular n-gons. So we're finally going to give those their proper names, and we'll look at the cycle graphs as well. So think about what the cycle graphs will look like. And this is a good example where the cycle graph and the Cayley graph really point the spotlight on different structural aspects of the group. So I think I'm going to leave it there. See you next time.